basic tasks in state machines. And mostly, even if the task is much more complex, actually the steps itself in the machine is usually like simple. You just have to find out all the steps, and it's a long term. The next thing is that now we programmed the PLC. We saw that how it's actually how we can execute code. Now we have to get the information from the field, and we have to communicate information to higher level systems in our factory. Now, looking at the connectivity at the field level, so that's from the PLC down to the field, down to the process. We have mostly three types of signals. We have discrete signals, which is just Boolean signals. The signal is either on or off, which is very typical in our factory automation. Then we have analog signals, where we get a signal for a size that is related to the size of the quality sensor. That means basically you get an analog signal, for example, 0 to 10 volts, that we somehow match between temperature range, for example. And then we have digital signals, which is a pulse of signal, basically giving us some digital information. So either you can transfer a number, or you have things like pulse width modulation, where you can see that it's like a percentage of a period that is active or whatever. That's a digital signal. And in factory automation, we mostly have discrete signals and digital signals. When it comes to process, oil and gas industry, where I come from, it's mostly analog signals. And actually, because analog signals kind of old and not enough anymore, we have in the process industry, we have analog signals, and they have modulated communication above the analog signal. So it's basically the analog signal plus some digital communication in the same one. So we can actually mix those signals as well. Looking at the input of a PLC, so somehow it's basically the same as you would see on a microcontroller. The only thing is that you have kind of more protection circuits. So we have the external signal coming to the PLC, and then there's like a protective diode preventing that you get too much voltage into the system. And you have a indicator's input signal, indicator that was the one that you saw on the I/O that was lighting up when the signal was positive or was off, when the signal was ground or not set. And then we have this protection circuit. Usually we use opto-isolation. So here the signal at that part, it's actually isolated. It's electrical, completely isolated. We have, the signal is passed into a photo diode, or into a diode, and only the light basically then surpasses the barrier towards a phototransistor. And that's why you can have different types of ground levels. So on this side, and this side is electrical, completely isolated because you have an optical barrier in between. That is also like the most expensive component in the I/O parts, because you have to, for each and every channel, you have to have these opto they're still cheap, but compared to resistors and LEDs, they're kind of expensive. And then you have the isolated signal, and that is then passed to the PLC. And so even if you would have like very high input surges on the voltage surges on the inputs, they won't directly affect the PLC because the PLC works in isolation, and usually also only the channel is destroyed, and as the channel has some protection, it should be very robust even against noisy signals. What we are kind of missing is the DC input unit usually also has like a low pass filter because there's like a maximum frequency that you could detect on the DC input, and usually you want to like shape your signal and get high at the too high frequency that you can't measure anymore. The same is true for basically the AC input. We also see that in the end we just have an internal signal in the PLC, and it's isolated, and because the signal has to be rectified before we can actually look at it, there you see this input rectifier. Usually we don't have lamps anymore, so we'll have kind of an LED indicator here as well, with a capacitor or whatever to keep the light on and not flickering at the AC frequencies. What does anybody know? What are the typical voltages that we use in 230 is a bit much for an IO.
I think you're AC.
No, AC.
3.3, 5?
5, that's typical for microcontrollers.
3.3?
3 is also typical for microcontrollers. So mostly it's 24 volts, 0 to 24. And if it's an analog signal, it's typically 0 to 10 volts or 4 to 20 milliamps. Can you imagine why it's better to have an input signal when it's an analog one that is 4 to 20 milliamps and not 0 to 10 volts? What happens with voltage over long distances cables? Yeah, it degrades. So because the cable has some resistance, the voltage will change when the wire is longer. And with current, there's no change in current. The current is the same everywhere. So that's why usually we have 4 to 20 milliamps instead of 0 to 10 volts. And then the next question would be why 4 to 20 milliamps and not 0 to 20 milliamps? The 0 to, or the first 4 milliamps is actually the current that the device can use itself, and then it modulates the last 16, the remaining 16 milliamps. But if you calculate that, so you have 24 volts maximum and you have 4 milliamps, it's like a very low power device. But for temperature, pressure, and so on, pressure management, that's totally fine. So you have the signal 4 to 20 milliamps plus the power supply on the same cable, which is helps to save some of the cabling. Okay, and I mean DC is a bit easier, from a circuit-wise, with a analog input we have the same. We would have an isolation here in between as well, but the analog circuitry is much more difficult because we just have, you must have like a linear voltage translation, and here we just use typically in the digital world we just have ones and zeros, and you would also have like behind the opto isolation they usually use something called a Schmidt trigger. Maybe you've ever heard of that. It's like a trigger that has a hysteresis. It just switches on, for example, it switches on at 18 volts, and then afterwards you need to fall down like to, I don't know, 6 volts or whatever, then it switches off again. So there's like a dead band in between that makes sure that you get a clear signal, even if it's like, because otherwise if you would be at around 12 volts it would switch on and off all the time.
What's it called?
Schmidt trigger. That's an electrical device. And so the main reason basically why this in and outputs are like more complex or more expensive than in a microcontroller. Microcontroller just has like a measurement device and that's it, a transistor, and here you have the protective circuits and you have like the shaping of the signal in that it's a that you get good looking signals instead of all the noise and everything. Okay, and you have the indicator as well of the state of the I/O, and that's true for each and every channel. Okay, if we go the other way around, we usually use two types of outputs. We have a relay output and a transistor output. And I mean, the transistor output is much cheaper, and it's also faster and so on. The only thing you have to keep in mind, depending on how the transistor, whether you have a neutral, no negative, positive, negative, or positive, negative, positive transistor, you like have the load on one side, so whether it's on the high side, on the plus side, or whether it's installed on the low side. And yes, there are also bipolar ones, but they are even more expensive. And then you have relays, and the relays, they don't have any direction, and usually they can handle more current, but they don't have as fast switching times as a transistor. So this is like the two types of output, but basically in most of the I/O we have transistor outputs. Okay, and now when we have analog inputs, I already said we have like an analog signal coming in, and now the analog signal, as it's like 0 to 10 volts or 4 to 20 milliamps, we somehow have to translate that into a digital value, because in the end we have to have a digital value in our code that we work with. And that is done by a so-called analog to digital converter. So that has the analog input comes in, and then for the example this one here converts that to an 8-bit output, and basically has steps. So like you have the analog input voltage, and depending on how high the input voltage is, you get a different binary signal, digital output from that analog to digital converter. And analog to digital conversion, that takes some time. There's different types of analog to digital converters. Usually, if they are fast ones, they tend to be less accurate, of course, and if you want to have slower ones, they can be more accurate, and if you want to have both, they get very expensive. So that's like, also if you have a digital oscilloscope, for example, that's like one of the most expensive parts in the whole electronics. Because there you have like, you want to measure accurately but fast signals. And because these signals, they are, because these signal converters, they are kind of expensive, we usually by now they are all like, they have conversion frequencies of megahertz or even more. And that is far more than we usually need in the automation world, because here we're talking about kilohertz cycles, so that's far more than we need. And that's why most of the analog systems, they are actually multiplexed. So you have multiple inputs and you have a selector for the input channel, and then they are converted one by one using the same analog to digital converter. But that has, in the end, it has the disadvantage that they are not sampled at the same time. They are sampled after each other, and we already heard that usually we want to have like a snapshot of the input state for control logic, and here we sacrifice some of the time by sampling the inputs one by one, but that makes the whole system a lot cheaper. And of course you lose efficiency or you lose conversion speed. That's the main thing. Then for I/O, we have to also create, that's the analog input, and they are the other way around. We also basically have a digital signal and convert it to an analog signal. There's different ways on how to do that, but the simplest version is that you actually create a PWM signal. Do you know what a PWM signal is? No?
That's what.
Yeah, also modulated signal. So you have like a base frequency and then a percentage of that frequency being on and the other percentage, the rest being off. And if you just send a pulse width modulated signal through a low pass filter, then you basically get an analog value. So that's like the cheapest version of an analog to digital converter, and they should be faster or more accurate. Yes, we do that differently. So, but in the end, I mean, we always have to work digital in our control system, in our software. And then the next thing is that we want to communicate information between components, and usually that's remote components, or like we have the PLC, and instead of having the I/O directly connected to it, we want to have it connected somewhere in the field. That's then our remote in and output modules, which is a very typical scenario where you have the PLC sitting in the cabinet, and then you have the I/O gathering gathering the information out in the field at a point where that is nearer to the sensors and actuators. And we have two ways of doing that. There's the serial communication, where we have bits sent after each other on one line, serial communication, and then we have parallel communication, where the bits are sent over parallel wires at the same time. And by now, mostly we avoid parallel communication, and we use serial communication. Does anyone know when there was like up to around 2000 we had a lot of parallel communication systems, not over long distances because then you need a lot of cables which would be expensive, but we really got better with serial line communication. Do you know what was like the breakthrough of serial communication? Fiber optic is actually, I mean, that's what we can use to go to higher frequencies, but like when we started with the internet, we used to have telephones and we connected the PCs via the telephone to the internet, and there they started modulating the frequencies, and it wasn't very fast, like the fastest modem, like 56 kilobytes per second. And after that, there came ADSL and then VDSL. And that was like a huge step forward because VDSL can by now create hundreds of megabits on the same old communication line. And this is just like that they were able to form the signals in a better way and then interpret the signals in a better way. And that's the same reason why we had, like in our PCs, we had in the beginning we had ESA bus systems. That's probably before you were born, and that was like the first bus systems that I was looking at in the PC. And then we had PCI buses, which were the first serial buses, but they had like 16 serial buses in parallel. And then came PCI Express, and there we actually, one line got so fast that they started with just a single line that was enough to get all the communication done. So here we have lots of things that can, we have lots of lines that's expensive. They're easily broken in the connectors and everything. And the next thing is if we communicate at high frequencies over lines and they have different length, then you get a shift in the signal, and that's not good as well. So that's why, because we can, we can shape the signals and understand the signal in a way that we can create single serial communications. We actually use that more and more. And that's actually also the reason why some of these cables, like you buy a USB cable, which is obviously a universal serial bus, why they can be kind of expensive if you buy a one that is like for high frequencies, then the cable needs to be ready for that frequency, and there's some technology in the cable itself. And then the remote I/O, the idea basically is we want to separate the PLC and the in and outputs in terms of where they are in the machine, and that's why we have a serial connection typically towards the in and outputs, and then we have a power connection. So in the end we would need 3 cables at least, but usually we have 4, or 2 and 1 optic cable. The reason why we use actually 2 twisted pair connections typically is that we use a differential signal. So we use the high level signal and the opposite, the low level signal at the same time. And if you like twist the cables and bring them to your from your source to your sink, then if there's any disturbance on the cable, it will usually affect both of the cables, and then you don't have a shift if you subtract the 2 signals from each other, because they are still affected in the same way. Fiber optic cables, they were very popular around 2000 because we were not able of handling electromagnetic noise, especially when there were a lot of drives and other electromagnets. By now, we are back to twisted pair with shields, and I think if the fiber optic currently the fiber optic I/O component, so actually creating the light and reading the light, gets cheaper and cheaper. So there will probably be some fiber optic cables in the future again. On the other hand, they break easily. We don't right now. We don't really like them in the automation industry. And the normal twisted pair cable is very fast. Okay, so when we have communication between participants, we somehow have to build up a network to transfer the information, and there's different ways on how to do that. So we have typical I/O networks: the star, the bus, the single highway, and the ring. And all of them are typically used in an automation system. So what is the star network? We have a central host component. And you get some settles next to it. Okay, and each of these endpoints in the stars system they are called a terminal. And if we map that to our I/O network, then typically we have that PLC sitting somewhere, and that is connected to a remote I/O. And that's where we typically have a star architecture. Okay, and so we have a central component and we have one-to-one connections to our other participants in the network, and they are the terminals of the network. If we have a single bus or highway, we usually have one line. That's our bus system. And we have the host and all the terminals connected to it. So that's our here we have our terminal again. And then usually we have like terminations at the end point. Termination of the bus. And the termination of the bus, so everybody is talking over one single wire, and usually you need this termination because when someone basically uses the bus, speaks on the bus, the signals are traveling both ways and they are usually reflected at the end of the lines, because the line usually is an antenna in the end, and that's why you want to terminate the signal at the end. When I was young, termination was very important, and still electrical is important, but by now it's actually surprising how good the systems work, even if you look at good termination. Okay, if we look at our automation system, we have the PLC again as a host. And then usually we have multiple remote roles or sensors and actuators. To that single bus. And then the last topology that we often have in the automation world is we have the ring topology, and there we have the host component again. And then we have like actuators just in a ring. So the host communicates to the first terminal, and that terminal communicates to the next, and so on. So the signals are always passed through the terminals until they are back at the host. And there we have a PLC. And that would then communicate, for example, an actuator, and a sensor, and a sensor. That's a little bit more as well. And the data is coming back. So the ring has basically it's like a closed, or no, it's kind of different because like the terminals sit in between. But if we would break the ring on one side, then they would be in a line. So the ring has some redundancy. One of the cables break, it could like go the other way. That's why they like to use it in automation systems. If we think of a Wi-Fi access point, what is a Wi-Fi access point? Is it a star, a bus, a ring? Just a normal Wi-Fi. Star, who is for star? Star. How many transfer medias are there in a Wi-Fi system? The transmission is done via radio frequency, and if we keep it simple, because actually there's like different channels and so on, but if we would have just one channel, we would just have one cable, that means Wi-Fi is a bus system. If someone is talking, the other ones have to listen. If two are talking at the same time, there would be only garbage. In reality, we have 14 channels and it's like 14 parallel wires. But, yeah. So this is about the communication connection in the end, so the media of transporting information. And in a star network, the host can talk to the terminals at the same time, all of them at the same time. Here you can just, one is talking, the other ones have to listen, okay? And here you can start talking, and then it will take one round till you get the answer, but you could already start talking again before you get the answer. So yeah, that's kind of a mix in between. The internet, so if we look at our Ethernet connections, the Ethernet connections used to be a line, because we had like, we were connected to a hub, and then that was just an electrical connection of all the Ethernet cables in one single hub. By now we have a switch. Do you know the difference between a hub and a switch? But now you can't even buy hubs anymore.
One just say you connection name, connection name with the other one that's more. So
the hub was just electrically connecting the cable, and that's why it didn't need power. And the switch now needs power because it's actually processing the information. So it's kind of a star, because the switch sits in between and you have one-to-one connections to all participants. The only difference why it's not like a complete star, if you want to talk to this terminal over there, then you send your data and the switch directly transfers it. But if there's multiple terminals talking to the same one, then of course there need to be some order on how to share the information. But from the perspective of a terminal, it always looks like he's directly connected to the other endpoint, which is nice for communication because then you don't have to take care of data provisioning. The backbone net of the internet, do you know the backbone net of the internet? Is actually a ring. So our internet is a ring, and it also works very differently. Like we have the kind of star network in our normal networks, that is the bus network for our access points, and there it's like an out of order, anybody can talk at any time. But the internet backbone is very structured. It's like a ticket running around, and you can only, or token running around, you can only talk to the neighbor when you have the token. So there we have structured information exchange. Okay, and to like organize that a bit more, that's like that was the structure in terms of how information can be exchanged, and then also kind of that needs to be mapped to a physical layout. And then we have an information transfer model. So we have this ESO-OC model. Did you ever heard of the ESO-OC model for communication? No? There was, because we had like lots of different types of communications, they were all proprietary. Everybody just created a type of network. And then if you want to have a more flexible communication and you want to reuse component, you somehow have to like have a structured approach on who is doing what. And that's why we created this ESO-OC model, and it's consisting of 7 layers. We have, when we start with the lower level, we have the physical medium, so that's, for example, copper that exchanges 1 and 0 through voltage, or fiber that uses optical transmitting. Then we have the data link on top of it, and that like creates packages or frames. Packages is frames of bits, for example, or frames of information, and is able to send not only single bits but frames of bits, and also makes sure that the bits are not changed on the transmission path. And you can actually, here you can address information, so you can address another terminal in your network. So here you have like data frames and addressing. But only addressing in a local network, so only a network that you actually know. And on top of that, we have the network and the transport layer. And network and the transport layer, did you ever heard of TCP/IP? So that's our IP, our internet protocol. TCP is our transfer control protocol, and TCP/IP is usually used in the internet. On this layer we have the IP layer, and here we have the transport layer, TCP layer. So here we can send data in the local network, and from here on we can send data in a worldwide network. The difference is here we have to know where our local partner is and what's his name in terms of a cryptic MAC address name. And here we use dynamic addresses, dynamic routing through the internet, and that's like the postal system where you can just write in an address and you send something to the US, and you don't know the way of your mail, but it will actually eventually arrive at the address. So that's like an international address, and that's like the local address. And then transport layer makes sure that when you want to send out information, it needs to be cut into standard sizes. For example, you have a big message, and it's like it's the same as you would go to the post and you have something you want to send out, and they just have standard post boxes. And then you have to like disassemble whatever you want to send and put it into the different post boxes. And then say this is piece number 1, this is piece number 2, and then send it out, and it arrives at the endpoint, and then here reassembles everything. Then we have session and presentation layer. Session layer is probably something you already saw when there's like session timed out and then your shopping basket is empty. So it's just meta information about the current connection. Presentation layer, that is, basically there you can adopt like the layout, whether it's, for example, the layout on your smartphone versus on a PC. You send the same information, but here the presentation is created differently depending on your screen or depending on your language. And also, here you can store in the presentation and session layer, you can handle all the encryption details of the connection below. And then the application is the final element where you have like a browser or whatever, and you look at your web page, and in terms of an automation system, that would be the application in a sensor or in the PLC. These layers, they work pretty fine, but we don't want to have presentation and session layers. And actually, we don't want to have network and transport as well. So we directly link the application to the data link layer. So that's not on field layer. So they are usually empty, doing nothing. Do you have any idea why this could be that you don't want to have this layer? It has to do with the real-time constraints. So basically here, if I want to send, like I'm in this room, A313, and I want to send the message to A315, I know that it's like the next 2 doors, and then I'm there, and I can basically calculate how long it takes to deliver the message once I leave the door. And if I send a letter, I hope that it will be in Germany delivered within 1 day, but maybe yes, maybe not. Here, the network here is dynamic, and you don't know when the message will be delivered, and that makes real-time communication extremely difficult. We still use that, because if we are in a local network, that's fine, like a local machine network, then we can do the direct connections and calculate all the timing. But of course we have multiple machines and we might have sites around the whole world where we want to exchange information, and then we have to use the upper layers as well, but then we are not real-time capable anymore. This is actually one of the things that is changing. I don't know if you've ever heard of time critical networks, TSN, time sensitive network, not critical. Because what we started when actually, I don't know, but it was, there were the first conversations using internet data connections. I don't know, somebody tool it worked horribly. And mostly by now we are, like when we use WhatsApp for calls, it works kind of good by now, because most of the backbone is actually time sensitive, so it can detect that this is, that when you use a service like that, speech connection, you need some channel back and forth to actually be able to speak. And it matters if the package actually arrives in the right order and so on, because if they are reordered, it doesn't make sense. And by now we have, so the backbone is working with time sensitive networks, and we now get more and more standard hardware as well that is able to do that, and then we can actually do real-time communication over larger networks as well. That would be quite good for industrial processes, and of course for us using internet as a telephone system as well. Okay, so we basically started in the automation system with just a central PLC, and everything was connected to it. And because cable are expensive and very unflexible, if you want to change something, we went from the central to distributed automation. And that was, here you see everything is distributed based on a field bus, and in reality we have remote I/O that still connects a star system, so that connects sensors and actuators. Here we would have the I/O, and then we have the sensors and actuators connected as like a central remote I/O, but so not all of our automation components are actually distributed, only the ones that are expensive enough. So for example, a drive or whatever, but a cheap light switch usually doesn't have an I/O. And also a switch or a button doesn't have an I/O, a digital one. It's so a field bus. You can do that, but I don't know, the switch costs like 10 cents, and then you need $2 or whatever for the field bus connection, and it's just not worth it. So that's why we have this layered architecture, and we also have old bus systems and new bus systems. So we have an automation system with distributed intelligence, because we can actually communicate. So there might be multiple PLCs exchanging information, and they can also use actuators like motors or whatever that are connected on the same network. And we can use, here we have Ethernet-based systems, so systems that are based on our IT technology, and they have one advantage: they can easily do the transfer to the internet, because they're basically the same technology, using the same technology. And then we have the old devices in our systems where we have dedicated field buses that collect the data to PLC, a data collection point, and then hand over the data to the Ethernet protocol based communication. We change, or the automation systems are now changing. Like about 4 or 5 years ago, there were more Ethernet nodes than Profibus or Profinet nodes than Profibus nodes. So this is growing very rapidly, and that's actually declining. The only thing is we have some things that we can't solve right now with Ethernet technology. So we use the standard Ethernet technology, but we actually extended that to so-called industrial Ethernet. We'll look at that in a moment. And so there we got rid of all the real-time problems and also mechanical issues and stuff like that that you would have on normal Ethernet parts. So that's kind of restricted, but still it's standard Ethernet technology with some extensions. And then we have, for example, we have problems with motion safety. That actually works by now over Ethernet, but we don't have any solution for X applications or for intrinsic safety explosive devices that are used in explosive areas. And right now, the problem basically is when you, if you have a field bus cable and you cut it, there should be no spark that is strong enough to ignite the gas or whatever you have in your surroundings. And that actually works in Profibus systems if they are X-safe. So there you can cut the cable and the energy is absorbed in the cable fast enough to not create any sparks. We don't have the technology for Ethernet yet. So that's why we still have like a mixture of both, because we can't support any use. We can't support all the use cases that we need in the automation industry. Could you imagine why we want to use EtherCAT instead of using our old traditional automations, field buses? Ethernet is communicating, field buses are communicating as well. Why not stick to the old field bus systems?
It's not as much faster.
Yeah, by now they are faster, but the yeah, that's the main thing. It's cheaper. So the IT stuff is just all over the world. They produce it in billions, and yeah, I think like the PHY chip, the actually control chip, is probably 100, 200 times more expensive. It's created with lower numbers. So yeah, we try to get rid of that just because of the cost. Okay, now one of the problems I said is that we don't have that on normal Ethernet. We have a problem with real-time capability, and that's why we extended the bus arbitration in the industrial Ethernet. And industrial Ethernet has, or there's three different things that they use. We have polling, time slot, and cyclic register. Polling means that like you have a master, and that's the only device allowed to talk on the Ethernet, and it polls the information one by one from the actuators and sensors. That is done, for example, by powering. And the good thing is it's very cheap to implement because you can just use standard Ethernet hardware, and just in the master and the PLC you have this polling software and it's coordinating everything. But it loses a lot of possibilities because it's just polling one by one, so there's only one connection open at a time, and you won't be able to communicate in parallel through the switch, which would be possible. You could actually access all the devices at the same time. So then we have time slots, that is Profinet. And time slots, there you distribute a clock to all your terminals, to all your endpoints, and they're all synchronized to that clock. And then you can say you have to sample your input at that time, and you distribute what you want to have for the outputs. And when the input is sampled, at that point in time, all the inputs, they just read in their inputs and transfer the current value in their time slot back to the PLC. And the outputs basically have an exact point in time where the output gets valid. Time slots, it works very well because there is I don't know if you ever heard of PTP? Not PTP, or sorry, Time Precision Protocol, TPP. PTP, point to point. So there's a protocol in the internet that we use actually to synchronize all our clocks. So you use it probably once you switch on your device. It uses a time server to get the time from the internet. And there we had that problem very early that we have latency in the cables and so on, and that's all handled by the time precision protocol. We can actually have nanoseconds accuracy distributing the time on the internet. If we want to have sub-nanoseconds accuracy, then it gets much more difficult. But that's by far enough for the use case that we have. With the time precision protocol, you can also measure things like the light speed, because you can measure how long a signal travels through a cable and comes back, and so on. And it's in all of our devices. It's available. And that's what. So Profinet basically uses a fixed time slot. The good thing is that you can communicate in parallel, have a dedicated point in time where in and outputs gets valid. The not so good thing is if there's like a additional device coming into the network, we have to rearrange the time slots. That's kind of an effort for the master, instead of just pulling an additional number. So it's not so flexible in reconfiguring. But the performance is very good. One problem is though that when it comes to very low, a very high cycle time frequency, or a very low cycle time, a high frequency in the cycle, we can't use standard Ethernet hardware anymore. We have to fall back to specialized hardware again. And then we have the cyclic register that is used by Ethercat. And the cyclic register is basically a ring. So the master is sending out an information stream where for the slave the input data is. So for all the terminals you have the input data. And you send that to the ring, and the slave just takes out the data it needs and puts back its output data, so that finally at the end the output data arrives at the Ethercat master. And that also works with very high performance and is, in terms of organization, much simpler than the time slot approach. By the way, standard Ethernet uses CD, which is carrier sense, multiple access, and collision detection. What does that mean? Every standard Ethernet device is connected to a cable, and it senses whether there is some signal on the cable or not. And if there is a signal on the cable, it starts listening, and if it wants to send out information, it waits till there's no signal on the cable. And then it starts talking, so that's the point multiple access, the point carrier sense, and then we have the access to the media. But the problem is we have multiple components, so there's multiple components on Ethernet, and if you think of like, they are all listening to someone who is currently talking on the Ethernet line, and then there's several devices who want to answer. They would wait till the one who is talking is finished, and then they will start at the same point in time. Once they found out that the other one is silenced, they start sending out their data all at the same time. And that would just result in garbage again. So what they do is they send and sense again at the same time. So they start talking and listen to themselves whether they can understand them. And as long as they can understand them, they say, okay, the line is okay, I can send out data. But if someone else is talking something completely different, then you will get garbage, and then they basically find out, okay, there's garbage on the line, and then all of them stop talking. But that's the collision detection part, so they detect the collision, and then they roll a dice, and that's the waiting time. And that's, for example, that's of course not, that's not real time capable, okay? Because if you have a bad dice, you will never talk. But that's how the internet is actually working, and it works very well in up to, let's say, about up to maybe 40 to 60% load, and after that it degrades very fast. Okay, so we have different implementations of industrial Ethernet, and behind all these, there's way more than just these three, okay? It's just representatives of different technologies. There's the Ethercat Technology Group. They take care of Ethercat and specify how Ethercat is actually working. And now you were in the lab and you were working with the Beckhoff TwinCat system, and actually the Beckhoff group invented EtherCAT, but they separated that into a public group because for them it's important that lots of vendors actually create sensors and actuators that could be attached to their system. So that's why they make that public, and that's why all of these different technologies in the end are competing again because the more companies you have providing devices for your network, the more attractive it gets that it's being used. And, then you probably sell more of your PLCs and more of your system again. So here they just have like you can read through the technology and how it works, and they take care about okay. If you are not a member of that, you just get the marketing material. But once you're a member and you want to create devices, then you get all the specifications that you have to obey. And when you created a device, then usually there's something called, how we call that in Germany, like integration party, where different device vendors come with their devices and then plug them all together and test out whether that's actually working, whether they're interoperable, whether they're working together. And then you finally, if you want to release your device, usually you certify your device that it's compatible with the EtherCAT standard, and then it gets the EtherCAT label, and then there's a high chance that it will actually work when you integrate it into the EtherCAT network. And also a high chance that you don't disturb anyone else in the system. So that's like maintained by the EtherCAT technology group, and you have the Profinet group as well, and the PowerLink group. And when I was young, there was like 7 or 8 big field buses, and I thought that with Ethernet they solved the problem and we get rid of all these different field buses because it's just annoying to buy hardware for a dedicated field bus. And then like all the companies came up with their own field bus because there it's with industrial Ethernet it got even easier because you now just specify something that is running on the hardware that's already there, so you don't have to create the hardware as well. Now I think we have like 25 or 30 different field buses. Yeah, it took some while, but the first of them are actually at 0 new devices, so they will run out of business after a while. But still, they will be around for still quite some while. What is important is that we can use this this industrial EtherCAT or industrial Ethernet with any from any vendor. We want to use that on different levels. So we want to use it on the factory level. There we have just normal IT. They use their, I don't know, Excel or whatever, and they probably should use a manufacturing execution system to control the plant better than just using Excel. But that's basically the upper levels. And then we have the process control level. From here onwards, it gets more and more real-time critical because here we really start controlling the process, and once we are on machine level, we have to be real-time capable. And now then you have lots of different devices. You have normal computers, mainframes, you have HMI devices. You still want to be able to integrate Wi-Fi or handheld devices or AGVs and so on. And then on the field level, you have the problem that here you have real-time capable devices, and you have also like safety devices that have to be treated differently. And that's why they created a kind of flexible protocol where they use normal Ethernet, normal Ethernet frames on the higher level. And then here at some point in time they switch from the normal Ethernet, which is not real-time capable, to this processing on the fly. And down here in this level we have this ring, and what they do with sending out the data, the data is never stopped at any device. So it's like you have a railway and you have stations, and the people hop on and off on the train while the train just passes through. And so that's the same here with the information. It hops on and off while the frame just passes through. And because of the frame is never stopping, you can get very high frequency, very low cycle time. Because basically it's just a few nanoseconds that each and every node is adding to your delay. Okay, that's like the EtherCAT frame processing, so the master sends out a frame, and even though the EtherCAT itself might look like a tree or whatever, you see that it basically just comes out and then follows the tree in a circle. So there must be an order where it basically hops from from component to component. At the end of the last component, it's then reflected. And in an Ethernet line, we always have bidirectional communication, so full duplex communication. You can communicate back and forth at the same time in the same cable. That's why it's easy to turn around, and then you go down to the next part of the tree, and you do the same until you basically reach back to the master. So the physical structure looks like a tree, the logical structure is always a ring structure. And now we have this data that is sent out into that ring, and mostly there must be some type of information on, you have a telegram with all the information for the whole ring, and then each and every slave knows, each and every device in the network knows which is the data that belongs to me, and he takes off the data that he needs and puts back the data that comes back. That should be sent back to the master, and then you have some structure in there, like there's PLC data, which is just the normal I/O data, or numeric control data, which is the data that you use for drives, and then you have normal data that is not real-time critical, like configuration data or whatever, that has a certain part in the telegram. And you see that it's limited up to 4 gigabytes. There's no more space than 4 gigabytes. So still there are some limits, and you have this Ethernet frame size of roughly 1.5 kilobytes per processing line. And looking at the ether, so if we have this 1.5 kilobytes, so you see that there's multiple frames actually that add up to 4 gigabytes. And if you look at how long a frame takes to be sent out on a 100 megabit connection, which was the standard connection for a long time in all the automation standards, because we could not easily go to 1 gigabit and so to 10 gigabits. I don't know if there's already 10 gigabit systems that are real-time capable. And if you calculate that, then you see that roughly a frame takes about 120 microseconds, and that's why it was difficult to actually get control loops that were faster than 120 microseconds. And that's why we actually, that's when they actually have, they they don't use the standard Ethernet technology anymore. You want to go to higher frequencies than that. Then now the Ethernet itself, if you want to send out data, you somehow have to create that EtherCAT data frame. And to speed up the process, they have these mapping, these field bus memory management units, and they're doing the mapping on this EtherCAT frame to allow a fast extraction and adding of the data to that frame. And this mapping actually needs to be calculated in advance, and we need some additional data for that. We're gonna see that later, because it's not like in our normal world. If you use usually if you use devices, most of the thing we do is like we configure something online. So you connect to your router for the internet and you configure it and so on. But if you have an automation system, usually the device is not existent, you haven't bought it while you actually create the software for it, so there needs to be some type of offline configuration possibility. And that's used also like to calculate these data frames. And then we have EtherCAT is actually by now, so there's like different types of standard. That's the old 100 base, so 100 megabit standards between the nodes. And the interesting thing is that they got so far that I don't know if you saw you saw the I/O of the EtherCAT, and it was like these single terminals, and each of that single terminals on the back actually is an EtherCAT device. So they use low voltage differential signals on the back. So basically EtherCAT here comes in and then passes each and every device, and each and every device is singly addressable, and then the EtherCAT comes out, and here it's from normal 100 base Ethernet, it's transferred to low voltage differential signal, and here it's transferred back to 100 base, and then you can basically connect the next device. But each and every card here is its own EtherCAT device. And that's something you can only do if the EtherCAT slave device is very cheap, then you can mass produce it like that. And that's actually the nice thing, that this engine that just runs through data and extracts and adds data is super easy to create and add as an electrical device. Okay, last thing, I already talked that we need to have some type of offline configuration, and the offline configuration comes, so if you have an EtherCAT device, you usually don't have that online like we did, where we scan for the boxes. You would rather search in a catalog for the device, because you don't have it, and there's a standardized format. Here they call it EtherCAT slave information, the easy files, and they are just loaded into the catalog, and then you basically drag them into your in your configuration, and then the process image can be calculated, because here it's like you have the device capabilities and you have the amount of in and outputs, and then you can just calculate how many bits in and how many bits out you have to reserve in the cycle. And so they use that information in the EtherCAT master, they pass that information and then create this
EtherCAT master driver driving the cycle over a standard Ethernet hardware. And on top of that Ethernet master, that was a component in our PC, runs the control task. That was what we actually were programming. And what we did was we scanned the Ethernet devices, and then they found the XML description and looked in the catalog on how to interact with them. And then we had this control task channel. That was the channel that we used to exchange our I/O. Okay, thank you very much. See you on Thursday.